Okay. Okay. So welcome everybody to this afternoon session. And we've all been enjoying this wonderful conference. And now we're from Chelsea, who will tell us about venturing to the boundary with braided module categories. So
Thank you very much. Thanks. I used AI to come up with that title. It's kind of cool. Well, first I'd like to start by thanking the organizers for putting together this conference. It's my first time in Bulgaria. It is so familiar and nice here. I really like it. So, okay. So this is a table of two equations. Many of you are familiar with one equation, maybe not so familiar with the other, but basically that is the whole talk. Basically, just two equations that we hope to find solutions for. So the first equation was motivated by work of Yang and Baxter in the late 60s, early 70s. They were interested in studying how particles scatter in a system without any boundary. So a toy model for this is you can take three particles labeled 1, 2, 3, and maybe you want to pass 1 by 2. Well, you can represent that with a symbol, R12, where RAB means passing particle A by particle B. And then maybe you want to repeat the process and pass 1 by 3 and then 2 by 3. We get this expression here. And what they notice that this is the same thing as taking the same configuration and first passing 2 by 3 and then 1 by 3 and then 1 by 2. And this equality of scattering patterns is represented by what's called the quantum Yang-Baxter equation, which I think everybody's familiar with here. So that is scattering of particles in a visible system without any boundary. What about if we threw in a boundary? So now let's fast forward to the mid-80s, mid to late 80s, due to work of Directly and Sklan. They were interested in studying how particles scatter in the system with a boundary. So as a toy model, let's just take two particles in a boundary, and we're going to represent basically bouncing against this wall with the symbol KC here. So we can pass 1 by 2 and then bounce 1 against the wall, then pass 2 by 1 and bounce 2 against the wall. And notice that this is the same thing as first bouncing and then passing and then bouncing and then passing. Now, this equation is represented by what's now called the quantum reflection equation, also known as the boundary Yang-Baxter equation. Not as well known, but we're interested in it for this talk here. So the goal of this whole talk is to study solutions to these two equations. We're going to do this categorically, especially this one here. All right. I would stop and ask some questions, but I'm not a physicist, so I'm going to keep going. All right. So in order to get at the category theory, what I want to do is swap out these scattering patterns and instead represent these with string models, because this is going to allow me to make some topological moves to get at these equations here. So I'm going to swap out these scattering patterns with now strings. Now, if I want to understand how this equality holds, what I can do is use two auxiliary equations, namely these things called braid axioms here. So these are two equalities of strings. And you can see why these are equal by just taking this pink string and dragging it down. Just dragging it down here. So these two equations are actually going to give us this one, which we can see by taking these two strings here, squashing them together, squash, and then dragging this crossing down, and then unsquashing. Right? Okay, so that's the left-hand side. What about this right-hand side? Can we do the same thing? Well, we're going to use some auxiliary equations. In fact, we're actually really going to need this one here. These are also called braid axioms, where, okay, basically we get these two equations hold by taking this pink string here and just dragging it over to the left. Just dragging it over, right? So in particular, if you have this one holds, you have this quality holds, and how do we see this? Well, we can take this string and just straighten it up here, and then take this passing and scoot it up, and then drag the string over. Okay. All right, so these are very useful axioms to have to get at these physical equations. Okay, so we're going to capture these equations now categorically. Now, what categories am I going to use? And you can probably guess what the first one's going to be. for this, I'm going to use the construction through Joel Street that was formulated in the late 80s, early 90s, called a braided modal category. What exactly is that? This is a category equipped with an operation, a five-functor that basically combines objects and combines morphisms here, and also an object which we are going to label as one, so that this triple behaves like a monolith. So you're going to have natural isomorphisms for sensitivity, natural isomorphisms for unitality, but I'm going to assume that they're all identities. In other words, that this monoidal category is strict because I want to draw pictures to do computations. So for example, if I have an object X here, I'm going to draw the identity morphism like so. If I have a morphism going from X to Y, I'm going to draw the morphism F like so. Now, half the people, when they do these computations, which is called graphical calculus, I would say probably more than half, they draw the morphisms going up, which I don't like because naturally you start at the top of the paper and you draw downward. So there's some discrepancies in the literature with this in any case. Morphisms are drawn like so. If I have two objects and I take their monoidal product, I can represent them by putting the strings side by side. And often the one I'm just going to leave blank here. Okay, so that's going to be the pictures I'm going to use to do computations. So that's the monoidal business. Now the braiding, as we know, is going to be a natural isomorphism that allows us to swap X over Y in an isomorphic way. And the components I'm going to draw with this overcrossing. The inverse braiding I'm going to draw with an undercrossing. So this has to be compatible with the monoidal product. In other words, you have some axioms that get satisfied, and these axioms are going to be precisely these, which we can write as commutative diagrams. So passing X tends to Y over Z is the same thing as passing Y over Z, X over Z. So many of you know this stuff. I'm just trying to wake you up from lunch. Perfect. Okay, but still, are there any questions on this? This is categories. I can answer questions on this. All right. So now what we're going to do is sort of represent this structure over here. And by represent, I want some sort of module category over this, which was mentioned in Head's talk. All right, so for this, I'm going to fast forward about 20 years to Berker-Brochet, 2013. I'm going to fix at the base a braided monoidal category and take a representation of it. So for that, I'm going to take a braided module category. So that's a triple. We have a category M. Now we're going to have an action bifunctor so that this pair behaves like a module over a monoid. So you have associativity, unitality, natural isomorphisms, which I'm going to assume to be the identity because I want to draw pictures. So everything in M, I'm going to write with a yellow line. And everything in C, I'm going to write in blue here. So X and C, M and M, this is an object in M, and I can just draw this like so. Okay, so that is going to be the module category bit. Now, what's the braiding? The braiding is going to be basically a natural isomorphism going from X acting on M to X acting on M, and its component is just drawn like so. So this has to be compatible with now the action bifunctor, and its compatibility conditions are represented by these braid axioms down here. So writing this down in terms of commutative diagrams, we can see these like so. So taking X tensor Y and wrapping around the pole all at once is the same thing as underbraiding, wrapping around the pole with the X line, overbraiding, and then wrapping around the pole with the Y line. And then this picture transfers over here. Okay, so that's what a braided module category is. Any questions? Okay. Keep going. So those are going to be the braided gadgets that I'm going to work with, the braided categorical constructions in this talk.
So when you write the symbolically with an M and a line, it could be a morphism in the category.
Yeah, I can take a morphism in here. Yeah, I can do that. You just have to like put it in yellow.
No, I just want to understand which picture represents.
Yeah. Any other questions? All right. Okay, so I'm saying braid. Of course, this ties to braid group representations. So basically, for every Coxter type, you have a graph, you have a matrix, you have a group, and objects of braided monoidal categories are going to be used to represent braid groups of type A. So here's your Coxter graph, type A. Your braid group of type A is represented like so. Many of you are less familiar with this. I think this is probably at least a quarter of the talks here in this group. And I can use objects and braided monoidal categories to produce representations of this group. Namely, if I take an object X in a braided monoidal category, I can form this group of automorphisms of X raised to the nth power here. And how do I get a representation of this braid group? Well, I just send the ith generator to the automorphism that swaps the ith and the ith plus first X. In other words, this generator sigma I goes to this picture. So objects in braided monoidal categories gives us representation of braid groups of type A. We can also use objects in braided module categories to give us representations, braid groups of type B/C. So here's the Coxter graph. Here's the braid group of type B. If you're not familiar with it, it has n-1 generators, denoted with sigma, and an extra generator T. The sigmas have the type A relations, and its generator T, it commutes with all the sigma i's going from 1 to n-2. And this is how it interacts with sigma n-1, has a degree 4 relation here. So now we can use objects of braided module categories, along with objects of braided monoidal categories at the base, to give us representation of this group. So what do? Well, we have two types of generators, sigma and T. I'm going to send sigma I to the same morphism that I had over here, which involves the braiding of C. But now T gets sent to an automorphism that involves the braiding of M. So in other words, sigma I and T get sent to these pictures. Any questions on this? Yes.
Sorry, maybe I missed it. Your category is, what is the structure of the arms? Are they?
Oh, this is just a plain monoidal category. So I'm not assuming linear or anything like that.
Okay, so when you say representation, you just mean.
Loosey-goosey, yeah. I'm just being like representation philosophically the way, yeah.
But
But representation,
not giving categories that are Boolean or anything.
not yet, no. But representation here, I mean, an actual group of them.
Yeah, okay. You have markers.
Yeah.
That's true.
Any other questions? Okay. So, and then you can kind of see these physical equations. I kind of want to keep those in mind, working underneath, working in the groups, if you will. All right. So just as a summary, I'm interested in solutions to these two physical equations, the quantum Yang-Baxter equation, the quantum reflection equation. I'm going to use some braided type categories to get at them. Here, objects are going to give us solutions of this. Objects over here are going to give us solutions to this. And of course, objects are also going to give us braid group representations of type A and B respectively. Now, of course, I can go straight from braid groups representations to solutions. I'm not going to do that because I like categories. So I'm definitely going to stick with this framework here. All right. So that's the framework that we're going to use to build results on. Okay, so now some results. Let's get concrete as I actually start to compute some things. Let's look at Hoff type solutions. So many of us know if you want a braided categories, a nice way of getting one is by taking a category of modules over a quasi-triangular Hoff algebra. So if you take a Hoff algebra, you take its category of modules, that gives us a monoidal category. Yeah, it's good enough, but in order to get something braided, an extra structure, we need to equip it with an element, say R, it's an invertible element, H tensor H, and it's going to satisfy just enough axioms so that it's going to yield a braiding on this category. So of course, this is called an R matrix over here. So what I'm interested in is once you have a quasi-triangular Hoff algebra, you get a braided monoidal category, and you come up with solutions to this quantum Yang-Baxter equation. I mean, you can kind of perturb this a lot to keep playing this game. So I'm interested in a notion of sameness for such solutions. So I'm going to say that two quasi-triangular Hoff algebras are braided Morita equivalent if their category of modules are equivalent as braided monoidal categories. So this is the type of sameness that I'm interested in for our next result. So there's a really nice result of Shimizu in 2010 that ties back to braid group representations. So what he proved was that if you take two finite dimensional quasi-triangular Hopf algebras, if they're braided Morita equivalent, their induced braid group representations of type A are equivalent as well. So if I take a quasi-triangular Hopf algebra, that H is an H module, so I can produce this type of braid group representation. So what this says is that if these two are the same up to braided Morita equivalents, these representations are the same up to representation equivalents, which I think is kind of nice. So basically representations of braid groups give us braided Morita invariants. So just as a baby example, if I take two finite groups G and G prime, I can basically make them be quasi-triangular Hopf algebras in a very easy way by taking group algebra and this R matrix here. And what I get is that when I take the induced braid group representation and take E here and scoot it over, and take the trace, I end up picking up the order of G raised to the nth power here. So the order of G is actually a braided Morita invariant of quasi-triangular Hopf algebras. That's what one would expect. This is kind of just a toy example to illustrate the types of invariants you could get. And now what I want to do is port that information over here. Any questions? Okay. All right, so in order to port over the information, first thing I need to do is start off with something quasi-triangular. Okay, start with something quasi-triangular. So I have to fix at the base a braided monoidal category, at least in the Hopf context. So I'm going to fix at the base a quasi-triangular Hopf algebra. And now what I want is a braided module category over H mod. So for this, I'm going to take what's called a quasi-triangular H comodule algebra. Now, the comodule algebra, that A is going to at least give us a C module category, like so. But what I need to do now is play the same game of equipping this A with an extra element to make this thing braided. Let me denote by K. This is going to be an invertible element in H tensor A, satisfying enough axioms so that this thing, which is called K matrix, gives us a braiding on M. And so this construction is due to tropes here. So basically, we have a nice module theoretic construction that's analogous to this over here. So we can get at solutions to the quantum reflection equation in a very concrete way. Now, once you have a bunch of solutions, you want to talk about when are these the same, some sort of equivalence of solutions. So we can talk about when two quasi-triangular comodule algebras are the same in this sense. So if I take two quasi-triangular H comodule algebras, AK and A prime K prime, we say that they are also braided Morita equivalent if they are equivalent as braided C module categories. So this is what I'm interested in over here. Now, first result is we want to come up with an analog of this result of Shimizu because I think it's kind of cute. I mean, I like it. And so this is a recent result with Monique Müller that came out this year. So what we need to do is fix at the base a quasi-triangular H comodule algebra. And initially what we wanted to do was just run the same game, take two quasi-triangular comodule algebras and come up with an analog. But the techniques in the paper, at best, we can only work with quasi-triangular co-ideal subalgebras, which are still important. I think they're still interesting. So in any case, let's take two bidimensional quasi-triangular co-ideal subalgebras. So these are like comodule algebras in each, if you will. If they're braided Morita equivalent, then their induced representations of the braid group of type B are also equivalent as well. So these types of braid group representations give us braided Morita invariants. Yes.
These ones we call it.
Yeah. Any other questions?
Examples,
Okay,
or is it going to either cause?
here's one. Here's a baby one. So I can take a finite group G and take some subgroups, L and L prime. Those are co-ideal subalgebras, and I can make them be quasi-triangular in this baby way. And if I run this game, I get that the order of the groups are also braided, Merida, and variance. So we actually classify braided, Merida, and equivalence classes in the paper for these types of groups. Basically, they are equivalent to conjugacy classes. And we also classify them for the Sweeter algebra as well.
What's the braid? What is the braid difference?
Oh, so we did it for the braiding where, okay, you have the trivial braiding, and then we also did it for the other standard one. That's like 1/2 tensor E plus 1 tensor G, that 4-term one.
So are they all non-trivial ones? That's what this.
Yeah.
Cool.
So this paper is really concrete. I think that this is actually going to be the most concrete thing I talk about here. All right. Are there any other questions? Okay, now we're going to go to the sky, which I like. Okay, so this is a framework that we're interested in. And if we wanted to deal with the Hopf case, we can deal with quasi-triangular stuff. Up to braided Merida equivalence, if you will. Now what I'm interested in is hooking up these categories, right? Because the objects give us solutions to these physical equations. Okay, so the way I'm going to look at these types of categories is by taking what's called a categorical center. So in type A, what I'm going to do is use a construction of Drinfeld, Joel-Street, and G, and it's really written nicely in Cassell's book, of a Drinfeld center, which many of us know. What this is a canonical braided monoidal category attached to any monoidal category, So let's go through its construction briefly before I hear it. So what does this thing look like? Well, objects, you're going to basically take your monoidal category and make it bigger, just big enough to be braided. So objects are going to be pairs where V is in V. And in the second slot, you have a natural isomorphism where V is fixed up here, but X varies. And you're going to swap X over to V. So X is free, so I can put X tensor Y at the bottom. That has to satisfy something, and it's going to satisfy that picture. Okay, so swapping X tensor Y over V is the same thing as swapping Y over V and then X over V. Okay, so those are the objects. Morphisms are going to be morphisms in C that are compatible with this natural isomorphism. That at least gives us that Z of C is a category. It has to be a braided monoidal category. So how do we form the monoidal product of these pairs? Well, if I take V, CV, and W, CW, its product is going to be the product of underlying objects in C. And this natural isomorphism has to be defined at X somewhere, and that's going to be defined by that picture there. I mean, I think this construction is really, really nice. So that gives us that Z of C is now a monoidal category. But this thing is also very naturally braided. So if I wanted to take VCV and swap over WCW, well, this is going to be a map going from V tensor W to W tensor V. The natural candidate is by taking this, what's called a half braiding, with W fixed and V at the bottom here. And that's going to be a morphism in the category. So that's a very natural way that we can take a monoidal category and force it to be braided. All right, so that's going to be the braided categorical structure in type A, if you will. Okay, now what about type B? Okay, so this is due to work of Robert Laugwitz, myself, and Milen, who was here. What we did was we mirrored this construction, set it up very nicely for monoidal categories, braided monoidal categories. So we have to fix at the base a braided monoidal category. Need something braided at the base. And what we're going to do is construct a braided module category attached to any module category. We're going to call this the reflective center, motivated by the fact that we're trying to get at solutions to the quantum reflection equation. And this is defined as follows. Objects are going to be objects or pairs where M is an M. And we're going to have a natural isomorphism where N is fixed, but we vary over X, and we form components like so. Now, again, X varies, so we can stick X tensor Y at the bottom. It has to satisfy something. and satisfies that picture. Okay, so wrapping around a pole with X tensor Y is the same thing as scooting this line over. Okay. So those are the objects of the category. Morphisms are going to be morphisms in M that are compatible with these components here. So that gives us that the reflective center is now a category, but now this needs to be a C module category. It needs an actual C on these objects here. So what's the action? If I take an object Y and C and it's an object, this pair and the reflective center, what's the action? Well, I'm going to have to form another pair where now Y is going to act in M, and now this, in the way of half braiding, has to be defined at X by something, and it's going to be defined by, what do you think? Another picture. This picture. Oh, surprise. Okay. So I think this construction is very clean because it's a clear analog of the dream belt center here. Okay, so this gives us a C module category, and it's also very naturally graded as well. So we need X acting on this pair to get sent to, I'm sorry, Y acting on this pair to get sent to Y acting on this pair, which is a morphism going from Y acting on M to Y acting on M, and the natural candidates take one of these components here. And this ends up being a morphism in the category. So we started off with an arbitrary module category over C, and we built something braided. Right. Any questions on this? I'm a little too fast. No? Okay. All right. No questions? So
This is generalized, it's reflective center. It generalizes this.
in the C, then very naturally, the E here is the double braiding. Okay, yeah. Thank you for asking.
What is E to the M, E to the Y triangle, M, I understand, but E to the M on the left side?
Pardon me?
E to the M, M comma E to the M. Oh,
E.
that's the final there, I saw it.
Any other questions? Okay, so let's bring this a little bit more down to earth, as down to earth as I can be, is to go to Hopf algebras. I can't do combinatorics or any of the hard stuff that y'all do. I can do a Hopf algebra, that's about it. So, okay, let's take a finite dimensional Hopf algebra. Its category of modules is monoidal. That's all it can be. We're not assuming quasi-triangular. We have, but if we take the center, we take the Drinkel center of this category, then we get something braided. So the natural question is, okay, this is a nice category. Is it equivalent as a braided monoidal category to a category of modules over something quasi-triangular? And the answer is yes, yes it is, yes it is. And the thing that works is this thing called the Drinfeld double of H. It is the best Hopf algebra. And I'm not going to write down the presentation. I will tell you that as a vector space basically is H star tensor H. It is the best Hopf algebra because it's a natural Hopf algebra that's quasi-triangular attached to any arbitrary Hopf algebra. So the Drinfeld double works. So tying this back to the result of Shimizu, if you take any two finite dimensional quasi-triangular Hopf algebras, you can talk about when their category of modules are equivalent as monoidal categories. Okay, so is there some sort of invariant of that type of sameness? Well, there is, if you consider the Drinfeld doubles of these Hopf algebras. So if H mod and H prime mod are equivalent as monoidal categories, the induced representations of the braid group of type A using the Drinfeld centers are equivalent. Okay. So everything ties together. So now we're going to mirror. Okay, now Hopf. All right, so now we have a nice braided module category attached to any monoidal category. What does this look like in the Hopf case? We're going to fix at the base a finite dimensional quasi-triangular Hopf algebra H. And now we're going to take an arbitrary finite dimensional H comodule algebra A, not necessarily quasi-triangular. So here we know that A mod is a module category. That's it, that's all we have. But we can make this thing braided by taking its reflective center here over H mod. So now the question is this equivalent as a braided module category to a category of modules over some quasi-triangular H-comodule algebra? So some quasi-triangular thing here, fill in the blank. Of course, the answer is yes, because it was no, like a stupid talk. But anyway, so the answer is yes. We construct this thing that's basically the analog of a Drinfeld double in the module theoretic sense, called reflective algebra of A with respect to H. As a vector space basically is H star tensor A. I'm not going to write down the presentation, but it actually is very concrete. You can do computations with it. And it's quasi-triangular. Has a very, very nice K matrix. K matrix looks a lot like the R matrix here, in fact, in a weird way. As we answered this question. Now, tying this back to the work with Monique, if you have now two co-ideal subalgebras of H, you could talk about their category of modules being equivalent as module categories. And now we get that if that's true, the induced braid group representations of type B, now using the reflective algebras, are equivalent. Any questions? All right, so we have the stuff that we're interested in, all these things we can play off of one another. We understand what these things look like in the Hop case. And now we have these categorical constructions to work with, the Drinfeld center and the reflective center. And in the Hop case, these constructions basically boil down to Drinfeld doubles and reflective algebras. Right. So now what I want to do for the last results is I want to talk about this notion of non-degeneracy. Why care? So braided module categories or braided nodal categories are important in their own right, but if you add in some extra flavor, they become really, really useful. So there are these constructions called modular tensor categories, which are basically braided nodal categories that are linear, abelian, finite in a way, but they also are what's called non-degenerate and ribbon. The reason why it's interesting to throw in all this stuff is because these are used to produce 3D topological quantum field theories. They have ties to subfactor theory. They have ties to topological phases of matter, topological quantum computing, a bunch of different things. So what we want to understand is, well, non-degeneracy is well understood on this side. So we want to introduce what it means over here, just to get this theory started. All right. So the notion of a non-degenerate braided monodal category, at least in a case where you're working with something linear. I mean, this goes way back to work of Müller in the mid-90s, especially in the semi-simple case. But what was cool was in 2019, Shimizu was able to basically unify all of these characterizations of non-degenerate categories in one fell swoop. So I'm going to describe that result and then describe what we did towards, putting it over here. Okay. So we're going to take a braided monodal category and we're going to assume that it's finite tensor. So that means linear, abelian, finite. Basically, this category smells like a category of finite dimensional modules over a finite dimensional quasi-triangular Hopf algebra, right? You just keep this in mind, or even like a finite group, if you will. Okay. So I'm going to take such a nice hoppy type category, if you like. And so what he showed was that there are various notions of non-degeneracy, or what it means for this thing to be non-degenerate, and they're all equivalent. Here's one notion. What you can do is you can take a certain subcategory of object X and C, so that when you double braid X with any object or Y and you get the identity, you get a nice subcategory of C. And you want this thing to be as small as possible. Basically, the monoidal unit and copies of it. This is often called the symmetric center or Weaver center, and you want it to be trivial. Okay, so this is one notion, what it means for C to be non-degenerate. Non-degenerate. And then amazingly, this is equivalent to another notion of non-degeneracy that looks nothing like this. So here, what you're going to do is you're going to take C, take its Dreamfield center and factorize it as a copy of C, braiding C, and C with the inverse braiding. Okay. In this case, we say that C is factorizable. In fact, if you take a factorizable Hopf algebra, you get a factorizable braided tensor category. So these two are equivalent, even though they don't look anything alike. And also, another characterization that looks different from these two is you can take the Cohen object of this category. This is actually a Hopf algebra in C. And what you want is that this Hopf algebra has a non-degenerate Hopf pair. So all three of these notions are equivalent, which is, I think, kind of amazing. I labeled this sheet so student. You have my name in the anyway. So what we're interested in doing is booting this over here. So, oh, before I get to that, some nice examples. Dreamfield level always, this category of modules is always non-degenerate. This is a factorizable Hopf algebra. So are small quantum groups. So this is, yeah, I mean, these are nice examples. Okay, so the analog. So this is joint work with my former student, Harshit Yadav. And of course, when we started working together, I thought, okay, let's just like, there's a fourth condition here. Let's just take all four conditions and like write down analogs and prove they're all equivalent. Let's just do it all. And then I forgot that, you know, it took like 20 something years for this theory to develop. So, you know, I had to like tamper down my ambitions, and we got analogs of 1 and 2. We showed that these two are equivalent, and then we showed that 1 and 2 imply 3, which was already really hard. Really hard. So let me show you what we got. So first off, we're going to do start off at the base, a braided finite tensor category. And if you're going to represent something, that representative must mirror what you're representing. So we're going to take a braided module category, which represents a braided monoidal category, but we want something to play nicely with this finite tensor business. So this M has to be linear and abelian, just like C is. And this notion of exactness plays nicely with this finite tensor business. I don't really want to get into what it is, but it's a technical condition that works well. So under these assumptions, we show that basically our mirror condition 1 is, instead of having this nice Cohen object here, we take a nice end object here because theory had been developed for this context. What we end up getting, this is an internal Hom, by the way. What we end up getting is that this is an algebra in C, and we're going to require that that has a non-degenerate pairing in a way. Again, I'm burying a lot of details here. Condition 1. Here, I'm going to want now, instead of the Dreamfield center factorizing, I'm now going to require the reflective center to factorize. So we have a copy of M here, and this category of functors. And if I take M to be C, I end up recovering these. So this is what it means for N to be factorizable. And we show that 1 and 2 are actually equivalent. And then here, what we do now is take all of the objects X and C, so that when you wrap around the pole and get the identity, the collection of all this subcategory, all such X, is equivalent to that. Okay, so we have a trivial symmetric center in a way. And again, if we take M to be C, this wrapping around the pole is the same thing as the double braiding. That's what we got this condition. So I like that result. It was hard. I like it because it was hard. Maybe, but so we have some examples. Reflective algebras are non-degenerate. And there should be one of examples. There should be. I find leaf theory to be kind of fiddly. I know that's going to break some of your hearts, but I find it really fiddly. I would love to be able to see this done, but there should be a slew of nice quantum group type of examples satisfying these features. Any questions? Yes.
So on the left-hand side, instead of taking finite dimensional modules, you all modules, that mean it's not nondegenerate.
Yeah, not actually, yeah, you lose tensor, you lose rigid, duals. But there's a lot of theory trying to get rid of that, yeah.
On the right side, demonstrate to prove, I mean, what the analysis make, yeah.
Oh, it fails? Oh, I can point you, I can point, yeah, I don't, we didn't show that it failed actually, but I can show you where the difficulty is. I think we actually might need to change this definition. I don't know how yet, yeah.
So what happens if you interchange the role of X and M? When you consider all M's,
Yeah,
these things happens for every.
so like, what does trivial mean, like requiring that this is zero, like that's the thing that I was kind of missing.
But in the examples where 1 and 2 are satisfied, what would be the other Z2? The Z2 of M.
We didn't study it carefully yet because we didn't know what it meant for this to be trivial. Like here, it's very natural to ask for this to be equivalent to that. Or generated basically by the 1 in C, but what is I guess the trivial object in M is 0.
Yeah.
And
Should be nothing.
yeah, it just seemed wrong. I didn't know how to.
True for RH of A.
Oh, what is Z2 of RH of A exactly?
The other Z2, the one.
Oh, the other
with
Z2, we
yeah.
didn't really work with that much because we got
Mhm.
stuff,
Okay.
yeah.
Mhm.
Yeah, that is, and actually, we spent months
Mhm.
getting stuff, so we were like, finally, let's just do this.
Mhm.
Yeah, like 4 months.
The condition exact, if you take C as the module over C, will reduce to finite tensor.
Basically, yes. Yeah, so exactness basically, what it's mirroring is that this monoidal product, if you hold one variable fixed, you have that the endofunctor is exact. Yeah, so you want that on both sides, and that's what this is mirroring. Yeah.
It is braided, monoidal, and one side is not, right?
Great, yeah, because you can put. Any other questions?
But you cannot just get away with for many of these things, what the essential property is right sides. This is not enough for you.
No, actually, in this work, we need both left and right exact, I'm remembering the proofs, yeah.
Take your example.
Yeah. But for many results, yeah, right exactness is good enough,
That's enough.
yeah. Okay, so, this is all the stuff that we were trying to understand. We have Hop case, we have the, categorical centers, we can go back to the Hop case with these constructions. We also discussed, non-degeneracy on both sides. And I could keep playing this game, I can keep saying, okay, I'm on side A, get a result, okay, drag it over here. Okay, let me get another result, and drag it over here, I can keep doing this, but I feel like something bigger is going on. So now what I want to do is share with you some speculations. These are questions that I do not have answers to, but I think they're just kind of cool things to think about. Okay, so some speculations. We have type A stuff, type BC stuff, but there are lots of cluster types. Many of them, A, B, C, D, E, F, elemental P, whatever. So, okay, here's type A. So you have group, you have graphs, you have matrices, you have groups for each cluster type. Here are all the graphs. Oh no, for types A, B, C, D, you have these finite types. You have affine types, Matildas. There are lots of types, and we only really zoned in on these two. And for each type, you have an attached group. You have an attached group. So once you have the graph that gives you a matrix, this matrix tells you how to relate generators of your group, like so. So my first question is, ignoring all the category stuff, can we always represent such groups with string models? So in type A, we can send our generator sigma I to these pictures that play nicely topologically. And type B, we also have a similar type of representation. But type D, E, and H, this kind of relates to your talk of, we do all types. Maybe. I wonder about this. I don't know. Yeah, it's one question. So another question. Lots of Coster types. Related to these categorical constructions, is there a type of braided categorical structure of type X? So that their objects actually gives us braid groups of type X. So I would consider braided module categories, braided categorical constructions or structures of type A. And I would consider these brochet braided module categories, braided categorical structures of type B. But what are the type of elemental B? Different types. I have some ideas, vaguely, but I don't, feel like there's something bigger, something bigger.
I think that they were braids on the cylinder.
Idea for that, but I haven't written, I don't know, yeah, I don't.
Considered cylinder, one is next to pen and braids.
Yeah, but I mean, what would that be exactly? I don't know. I don't know. But for sure, I know 10%. Okay, next question. Related to now these physical equations. Okay, this is just kind of really punching up. Can we use objects in these braided categorical structures of type X to model particle scattering and physical systems with obstructions? So, okay, in type A, we had no obstructions. In type B, we had a wall. What about type C and D, etc.? What happened? How are we? And then, okay, here's the good question. I was interested in type A. Coming up with solutions to the quantum Yang-Baxter equation. Type B, coming up with solutions to the quantum reflection equation. Okay, type B, of course, is there an equation? One equation to rule them all. One, I don't know, and this is, I really don't know the answer to this, but this is just, late night thoughts that I thought I'd share with you. In any case, thank you very much for listening. Here's some shameless advertisements for students today. Thanks.
Oh. But Chelsea, I think was the first one to finish like 2 minutes early. So, yes, so any questions for Chelsea?
Lots of questions during talk.
I think one sort of general, is there a sense in which you can get the sort of boundary by folding type A? Sometimes business being big in terms of a boundary is really a mirror and something. Things interacting really usable.
Yeah, but it'll kind of have to fold, not like, but kind of like happen like a little bit. Because it's not like type B is not exactly symmetric.
Type A is, type B, type C patch is something you get by folding type A with quite a lot.
Yeah.
Probably.
Oh,
So you imagine sort of just symmetric interaction.
I don't know. I can't picture it. I mean, maybe, yeah, I can't quite picture it yet. I can actually see that for type D in a way. D, yeah. Actually, type D, I can see that. But yeah, something to think about.
So, I mean, really, how does the I quantum group come into play here?
Pardon me?
Does the I quantum group come into play?
That's related, yeah. I mean, like you.
That's the part,
Yeah, that whole industry is very much related to this braided module category business and quantum symmetric pairs and all that, yeah. Yeah.
If not, let's thank Chelsea again.